No, just to look at those things. Okay. Okay, just 2 more lectures to survive. I don't think, by the way, we're going to have a discussion section this afternoon. None of you are planning to be there, I know, so maybe we can have discussion right after the second talk. So last time I basically went through this contradiction between things we would like to be true and discussed, the unpleasant consequences of giving up any of them. So, I don't know, right now the situation's a little bit like the situation I described before ADS-CFT when we had these 3 unpleasant alternatives, remnants, 3 unpleasant alternatives, and none of them seemed like they could be right. And I feel like we're pretty much in the same situation now, and so we need some bolt from the blue, like ADS-CFT, to come along and tell us what the truth is. So that's something to look forward to. So I have 2 things I want to talk about. I finished up last time describing this one form of quantum drama to give an example of what it takes apparently to try to avoid the firewall. And there are other examples, and rather than discuss them directly, what I want to do is I want to talk about some other things. And a couple of these things will come up kind of naturally. So the 2 things I want to talk about today are well, I'll call it precursors, or bulk reconstruction maybe is a more common term these days, and chaos. So we ended up last time with, again, this apparent paradox. Now we have this magical machine, ADS-CFT duality, which is supposed to be a complete theory of quantum gravity and answer all questions. So we should ask ADS-CFT, is there a firewall? The problem is ADS-CFT is kind of oracular. You have to ask the question in the right way, and then it gives you an answer you don't necessarily understand. And so we don't know. First comment is, you might think something as dramatic as a firewall would have some kind of very strong signature in the dual CFT, but it doesn't necessarily, because remember, there's this gravitational redshift. GTT is going to 0 at the horizon. And that means that something that has very large energy near the horizon can have negligible energy in the CFT. And so there's no reason that, so there's no guarantee that something dramatic near the horizon would look dramatic in the CFT. The other thing is, as I discussed last time, basically in a black hole the CFT is thermal. All thermal states look more or less the same. And so what exactly is one looking for to answer this question? So what I want to do is to back up to states without black holes and ask the corresponding question. So here's the CFT, the boundary, and the bulk is in here. And suppose I give you a CFT state, and I don't tell you how I've prepared it, another one of those homework problems. And I ask you, okay, here's the state. What is going on in the bulk? What's the machinery for answering that question? So there's this basic dictionary due to Gubser, Klebanov, Polyakov, and Witten, which relates the boundary limits of bulk fields to local operators in the boundary. And so if in the CFT you see something that looks pretty much like vacuum, but that has, local excitations, then what you know is that in the bulk there are excitations which lie, just right at or close to the boundary. But that's a very special case. What about if I've, thrown something in a while back, so it's now in the center? So we can kind of follow this via the time development, namely, so I create a state at the boundary and then it propagates inward. In the CFT, what's going to happen? So a typical operator that we're talking about here, it's a composite operator. It's not a fundamental field. The simplest thing would be something like trace of f mu nu, which even in free field theory creates a pair of gluons, whatever, and then they will move apart in general. And because it's a strongly coupled theory, it's much more complicated than that. These things will interact and fragment. And so roughly speaking, the answer is that as this moves into the bulk, the excitation in the CFT gets larger. And so if you see some kind of coherent excitation over some distance scale, you can more or less infer that there's something going on in the bulk. Okay, now we can make that more precise. And so there's a technology which has basically been around since right after Wan's paper to do this. There's 2 or 3 steps depending on how far you want to go with it. So again, all of my bulks will. Well, actually, I want to take this. This is the picture at one time. So now let me take that picture and add time to it. I'll need time. And here's our point in the interior. The first step is to integrate the field equation sideways. To the boundary. So step 1 is to integrate the field equation sideways. Okay, now this is not a Cauchy problem. Okay, this is actually not something that has a good. This is not a good thing to do with the differential equation, and in fact, in this case, what it does is there are multiple solutions to this, which look inequivalent, but actually because ADS-CFT, because ADS-CFT actually constrains the boundary data, they turn out to be equivalent. And I'll be more precise about that in a little while. I'll give you a very concrete example of this. But let's pretend we know how to integrate field equations in a space-like rather than time-like direction. That's the first step. The second step is once we get to the boundary, we use the GKPW dictionary to replace the field in the bulk with the operator. And so the net effect of the first 2 steps is that the bulk field, I'll use Z for the depth and X for the position in the other directions, is represented as some smeared version of the local operators. Smeared in both space and time. This kernel for this, the Green's function for this integration, of course, will be smeared in both space and time. And actually, the field equations are nonlinear. There are interactions in the bulk. And so there'll also be higher order terms. This often is referred to these days as the Cabot et al. Construction, although it was largely outlined. They've refined it in many ways. It was largely outlined right after Wan by Banks, Douglas, Horowitz, and Martin. Anyway, bunch of old guys. Yeah, question?
I'm a little confused about the context. You begin with start with some state of the CFT.
Yes.
But then you started talking about some gravity geometry.
Well, sorry. Yeah.
You require some assumption of
Good. Excellent. Okay, thank you. Actually, sorry. Thank you. So this is a very good question, which as with most of John's questions, is several minutes ahead of time. John is a causal, but it's a good one to point to now. So yeah, but because in fact, to integrate the field equations, I'm integrating. Sorry about the very bad use of the blackboard here. To integrate the field equations, I'm integrating in a background, and for simplicity, assuming the background is standard Sitter space. However, because of the nonlinearities of the bulk field equations, because we get these higher terms, in fact, this construction is background dependent, at least to a limited extent, because if we shift to a different background, it means we're shifting the vevs of these operators. And that shift of the vevs of the operators is just shifting this to a new background. So there's a limited degree of background dependence built into it. Now, the question is how much? Because this is, by the way, this is a series. It's a series because the general principle in ADS-CFT is the bulk interactions are of order 1 over n. And this series, okay, well, my own expectation is that you should think of this rather than being as a series, think of it as more an analytic continuation where you go from one classical background to another. And I think that by sort of process of analytic continuation, you should be able to carry this construction to basically any background. The only known, so with analytic continuation, you can sort of, again, you start with a construction somewhere and you function somewhere and you move it outward until you reach a natural barrier, a true singularity. And the only natural barrier I know for this construction is a black hole horizon. That is, this construction fails to work once the field phi, once you've changed the geometry enough that you have a black hole, and moreover, once the field gets behind the horizon. I'll talk about why it fails there. Lots of questions. You have your hand first. The domain of integration, well, is the boundary, but actually because this integration process is non-unique, you can restrict to different subregions of the boundary. The simplest subregion would be all points space-like with respect to your desired point. That's the simplest one, but there are other choices. So, question, Laura?
So I just want to make sure. You said that you get a problem when you hit a black hole. Is that a coordinate independent state?
Good. So, so there'll be in a sense, yes. That is, there will be an obvious problem with this construction. Maybe it's improvable, but there'll be an obvious problem with this construction as soon as basically this is behind the event horizon. As soon as it can know, I mean, you can kind of see what's happening. You're using the ability of this point to send signals to the boundary to reconstruct it. As soon as you lose that ability to send signals, this construction fails, and you need to be cleverer. Was there another question? Yeah. Go ahead. So the K's are something like Green's functions, and they're not. So you know there's the various bulk to boundary Green's functions. They satisfy the same differential equation. They don't have the same boundary conditions, so they're in the general class of the bulk to boundary Green's functions. This one, because it's basically been built out of sort of interactions, is like the product of 3 Green's functions integrated, and so on. Okay, so good. Now there's a third step. So these 2 steps you can do rather explicitly. There's a third step you can't. But if you want to answer the question in the terms I posed it, I gave you everything at basically a single time. Here things are smeared over time. Let me actually draw now. This is a different. This is the CFT, and this actually well. Maybe we have some context in which the domain of integration x prime looks something. It doesn't matter. Just I picked a random shape here, but if I want to express this in terms of operators at a single time, I can integrate the field equation in principle. This step assumes that we have the power to solve the conformal field theory. It's interesting to kind of make distinctions between questions we can answer just knowing the CFT exists, like information not being lost, and questions that would require us to solve the CFT, like this one. So if we could solve the CFT, so this is sort of an existence proof, we could integrate this operator back in time. And because it's a composite operator, again, the constituents spread out. And so this operator becomes some operator which is, instead of being a local operator in space-time integrated over a space-time region, it becomes a genuinely non-local operator in space, something like a Wilson loop. We call it a Wilson loop because it's non-local and gauge invariant, and we're not very imaginative, and all the things we know of that are gauge invariant and non-local are Wilson loops. And so the third step is to integrate the CFT field equations integrate the CFT field equations back to t equals 0, say, or whatever time we want. And so so now we have some non-local gauge invariant operator in the CFT, which is the answer to that question. So this is a construction in principle of the answer to that question. It's unsatisfactory in a number of ways. So one of them is it assumes the ability to solve the CFT, but that's part of the price of ADS CFT that you're at strong coupling. But also, it's kind of ugly that we have to actually by hand solve the field equations in the bulk that there's not something more intrinsic in the CFT that tells us that space-time exists and how to measure it. Maybe there is, and we haven't figured it out yet. I'll come back to that in a second, but let me just so now why does this fail at the actually I guess we're in ADS here. So the reason it fails I've already mentioned, but I'll draw the picture. Once your point is behind the horizon, this process of integrating to the boundary runs into the singularity, and so you don't know how to carry it forward. Using the ambiguity of the construction, you can do something a little different. You can first integrate backwards in time, and then once you've integrated backwards in time far enough, you can integrate to the boundary. And this works for young black holes, but eventually you run into this blue shifting problem where you lose control of the physics. So this construction actually kind of works for very young black holes before the scrambling time, but doesn't work for most black holes. Okay, so you see, really, it doesn't seem like the kind of construction that's going to answer the question we want to answer, because it assumes that we understand the bulk dynamics, that we know the field equations, that we actually know everything we have to include. So this is useful for answering the question as posed. That is, I give you the state, you need the decoder. But it's really not useful for understanding physics that you don't understand. So now what I want to do is, I guess, two things I want to mention. So one of them is another form of quantum drama. So Papadopoulos and Raju have made a proposal for how you sort of see the interior of the black hole in ADS-CFT, and also how you see that it's not got a firewall. And the first step in their construction makes the following observation. So, as I said a couple lectures ago, or maybe last lecture, in thermal equilibrium, all states look basically the same. So if I take a state at random from the Hilbert space, and I look at the statistics of this mode B outside the horizon, they will look thermal. Just general principles of thermal equilibrium. It's also true from the Hawking calculation. So typical states have B thermal. It's also true from the Hawking calculation that if the inflowing state is vacuum, B will be thermal. So this seems pretty good. From the outside of the black hole, the thermality of B is consistent with typical states of the black hole having smooth horizons. And so Papadopoulos and Raju have basically tried to build the interior Hilbert space starting from this point. But and again, this is one of these ideas which I put in the class of Technicolor again, which are pretty cool when you first see them, and as you poke on them, they don't seem so good. So there's something funny going on here, because typical states have infalling vacuum. That's the first thing. That's a good thing that we'd like to have. But also, because they've constructed in some way these interior field operators, these interior field operators create large numbers of, for every typical state, every vacuum state, they create a whole spectrum of excited states. So typical states have infalling vacuum. Associated with every vacuum state, there is a whole set of excited states. Now, there's a packing problem here, because on the one hand, almost all states are typical. That's the definition of typical. So almost all states are vacuum, but for every one of these, there are many excited states. So there's a mismatch. Are there more of these, or are there more of these? How do we pack in for every typical state a large number of atypical states? And the way you do it is that you have to relax the usual rules of quantum mechanics. So the usual rules of quantum mechanics are that, in particular, if I have two states that are physically orthogonal, if in this state an observer sees definitely an excitation, and in this state definitely not an excitation, these are mathematically orthogonal. And that's associated with the Born rule. It's a basic part of quantum mechanics. In order to sort of pack everything into the Hilbert space in the way they want, Papadopoulos and Raju have to squash things. And this is something that Don Maroff and I have made precise in a very recent paper. They have to squash things so that states that are physically orthogonal are nearly parallel in the Hilbert space. That's how they solve the packing problem. So in other words, the things that you would measure to distinguish these two states are not ordinary linear operators, because ordinary linear operators have this property, and so they call this construction state dependent, because what it really means, what these words mean in their context are not just background dependent. If you multiply two linear operators, as I've done here, you still get a linear operator. Their observables are nonlinear on the Hilbert space. Now, this may be a feature rather than a bug. It may be that to make a theory of quantum gravity, we actually have to relax the rules of quantum mechanics in this way, which would be really interesting. We would have learned something really interesting. But in looking at how one tries to implement it and how much one gains in relation to how much one loses, my personal verdict for this idea is Technicolor. Okay. But this is a second kind of quantum drama. Quantum drama in which this basic rule of quantum mechanics is modified. Question?
Are those two states on the right, are they two typical states or states?
So let's say one would be a typical state and one would be an atypical state. So I said physically orthogonal. So say one has an excitation and one has no excitation. So the no excitations would be your typical state. This one would then have, okay. And the only way that you can arrange that almost every state has no excitations, but there's room for the states that have excitations, is to squeeze them in like that. Yeah.
So it may be a naive question, but I mean, if you had the situation on the right, you could just imagine applying, Gram-Smith and coming up with a non-north basis. I mean, what's
but you can always make the point is it's the connection between the mathematical state and the physical observation which is not linear. And so, for linear operators, if you know their action on every member, for linear operators, if you know their action on every member of an orthogonal basis, you know the operator. Here, that's not true. You actually have to specify separately its action on every single state because it's nonlinear. Yeah.
If your operation is nonlinear, then what does it mean to say that you have a base? I mean, it's not a vector space.
That's right. Well, yeah. This is. I think if you're going to change, okay, so right, so maybe this is a feature, not a bug, but it means that you have to rethink a whole lot of stuff to make a consistent theory of measurement, and they don't. I think that I don't see that. Yeah. It is confusing, and I think when you start again, it's designed to produce this output, and now if you start asking it more intricate questions, it actually doesn't exist yet for those more intricate questions. Yes, John? I mean, what they're doing, I guess, I'm not sure. I mean, I think that's what I sort of said when I said that from the outside, the statistics of everything is consistent with a smooth geometry. That have smooth geometry? They want to say typical. They want to, ignore the stuff outside the black hole because they want to say that typical states do. That Haar random states have a smooth interpretation. But okay, then you're a believer in the firewall because.
That's right. A typical state of the CT
Okay.
has a dual, which is just a big mess of junk that's not a geometry.
Okay. Good. Then, I don't know if we agree or not. I think it's very radical. But okay, that's good. Yes, you would kind of exactly. You would. I mean, I guess this is sort of one of Don's roots to the firewall. Just the notion that in the Hilbert space, the geometric state should be rare, not typical. But what you said violates low energy effective field theory for gravity, because low energy effective field theory for gravity, no matter how you prepare the black hole, if you leave it alone for a while, the adiabatic principle will bring it back to vacuum.
Energy eigenstates, the local Hamiltonians are not typical states.
Sorry. No, they're not. I didn't use energy eigenstates. But sorry, Tom. Well, but no, in the low energy theory, you've always integrated. Well, I guess I would say you've always integrated out the short distance stuff, meaning it's the Born-Oppenheimer approximation. The high energy stuff is sitting in its ground state, subject to what the low energy modes are doing. So it's Question.
When you're talking about typical states here, I think there would be two. One idea is this idea that you have some lattice, so much spin, typical.
Yes.
That's not going to give you nice.
Well, so right. So there's this notion of kind of Haar typical. So basically, you just have a state vector, and it's somewhere on a giant Hilbert space sphere, and you pick a direction on the sphere.
That's not what you mean by typical.
Pardon?
That is a much more horrible thing.
Well, actually, Actually, I'm going to assert that within the microcanonical ensemble, meaning my choice is limited to some range of energies in the CFT, a randomly chosen state will look like a black hole surrounded by a smooth geometry.
But that's very different than Haar random on the whole.
Oh no! I'm not doing. No. It's always on a bounded ranges of energy. Sorry, no. Haar random wouldn't even be defined because it's a Haar random from an infinite space. Right. I guess this is important, of course, because once you specify Hamiltonian, you've really put in a lot of sort of restriction on things. Good. I guess this comes up in your picture. I think you drew a picture with a very tiny Hilbert space and a bigger Hilbert space and a much bigger Hilbert space. Right. So this is Haar random restricted by energetics, so it would be one of the smaller Hilbert spaces in your language. Anyway, I sort of want to move on because I have other things to say that are more fun to talk about. So the second thing, though, the last thing under precursors is the following. So what I've described here is kind of 20 years old, and it's been refined in moderate ways. But recently, Harry, Dong, and Harlow, and then Harlow, Preskal, Pastowski, and Yoshida have given an entirely new way to think about this. And the first thing they focus on is this ambiguity in the prescription. So in particular, and I think that was it Mark who drew this picture? So now suppose I want to talk about this construction for the field in the center. Then what's known is you can take any sort of contiguous half plus a little of the CFT, and that's enough to reconstruct the field there. And again, that's consistent with what I said above. It actually it's related to the ambiguity in this process of integrating sideways. But they have what may be a deeper way to think about this. So let's actually think about separating the boundary into sort of 2/3, 2/3, and 2/3. And so these two, so there is, I should have just called them A, B, and C. So any two of A, B, and C, if you have the state in any two of A, B, and C, you can reconstruct the field at the center. And so that's interesting because that means you can delete any one of the three. And still reconstruct the state in the center. And so the information about the state is very delocalized. You can just simply throw away a third of your boundary, up to half of your boundary, and still reconstruct the state. Question? Pardon? Oh, you can throw away 1/3. You can throw away 1/3. Sorry, if I said 2/3, I meant 1. You can throw any 1/3 of your boundary and still reconstruct the state. Now, this is very much like quantum secret sharing, where you have some quantum message and you give pieces of it to 3 different people, and any 2 of them can reconstruct the state. And so it's a pretty remarkable reinterpretation. But there's something funny about it. So with quantum error correction, the secret of it is that you use many bits to encode 1. So that if a few of the bits are deleted or randomized, you can still recode the message. So this only works in a subspace of states, which they call the code subspace. But actually, they've recently, and so this seemed unsatisfactory. And Eric and Vladimir Rosenhaus and I tried to reinterpret this in a more conventional language of gauge invariance, where you simply got everything out of gauge, where the subspace that you need to focus on is the space of gauge invariant states. And I'm still not sure whether that's a useful point of view. There's some things about it that are nice, but in the second paper, this is going to be kind of a cartoon. But I don't want to be drawing all day, so data. There, you get the idea. So they draw one of these Mera-like networks. I don't want to say Mera-like, but you see lots of these pictures today where the state in a field theory is encoded in some kind of hierarchical contraction of tensors. And they do this, but what each of these nodes is again some kind of quantum error correcting code. And unlike Mera, which just builds the ground state, they have on each of these nodes a leg hanging off, which has a state that you can specify. And so what this whole network is, it becomes a map from the bulk Hilbert space into, not onto, but into the boundary Hilbert space. And again, it doesn't have the energetic motivations of Mera. In fact, so far it doesn't have much structure at all except for quantum error correction. But again, the idea is that it gives them a way to basically take the state in the interior and push it to the CFT, and within so again, this maps to a subspace of the boundary CFT. Within that subspace, the code subspace, they can construct these field operators. And where, again, we tried to reinterpret this code subspace in conventional gauge invariance terms, their interpretation is the following. So this question, what is the field in the center, only makes sense if there, well, you have to think about what you mean by that question if there's a black hole there. We've explained why it's hard to push this behind the horizon of a black hole. And so their code subspace simply consists of all states in which there's no black hole in the center. And so the quantum error correction works because the subspace of states in which there's no black hole is much smaller than the subspace of states in which there is a black hole, and so there's room for this quantum error correction. It's quite clever. It's, like I said, the first new thing in this subject in 20 years, and there's kind of a very nice challenge that they've outlined, which is the following. So I said, what if we have more than half? So I focus on having more than half of the boundary, but what if we have a non-contiguous more than half? We have that part, and we have that part. The conventional construction above only gives you the so-called causal wedge. And doesn't reach the center. It has no way to reconstruct that point. In fact, there seems to be a good argument that you can't reconstruct that point because this by bulk locality, this operator commutes, at least perturbatively, with everything actually here and here. So there is something intrinsically non-perturbative about this construction. But their claim is that, at least in this framework, they can basically because this construction doesn't make use of something which within the code subspace, this small special set of states, there will be some particular restricted form of entanglement between the upper region and the lower region. And by taking account of that additional information, you can construct a larger region of the bulk. So and it hasn't been done explicitly yet, but I have to say, a lot of these Mera-like pictures are very coarse. This is an entire ADS volume, and a string is really tiny on this scale. So it's a very crude model. But I think actually they've identified something that goes far beyond this individual model and is probably true. I fear I'm likely to lose a bottle of wine on a bet on this. I've never lost a bottle of wine on a physics bet before. But I fear I'm going to lose a bottle of wine on this. But I'm happy to, because it really says that we've learned something it highlights the importance of entanglement. It's a more complete reconstruction of the bulk. Maybe also it is more intrinsic, as opposed to having to put in the dynamics. It may come out. Now we can ask what happens about inside the black hole. So this construction was motivated by Papadopoulos and Raju, but Dan was very careful to put a line in his paper. Note: we do not violate quantum mechanics. So in its current form, we'll see. This is a work in progress. So whether this is if this is as good as I hope it is, it will teach us how space emerges. If it is, it will teach us how space emerges from the dual theory, and maybe that will answer the other question. Yes?
So
Yes. That's right. That's right. Yeah. I'm hoping that one can look at the CFT and say, oh, this is entangled to that. Therefore, we have a... Yeah. Now, I have to say, there's this problem, and Juan said this, I think, in the first lecture of his talk, that entanglement is not... Just as Papadimos and Emergius operators are not normal observables, neither is entanglement. And so it would require something more than entanglement. Entanglement plus large N factorization, something that guarantees a semi-classical structure. So it would be more than just entanglement, but entanglement would be an important part of the prescription. Okay, so I'm going to move on. This is perfect. I have just enough time for part 2, which is chaos. So there are 2 papers, two things in the last 6 months that got me very excited. One of them, obviously, is this error correction, and the second one is quantum chaos, the work of Kitaev and others. So, again, let me go back and review some statistical mechanics, classical statistical mechanics. So here's phase space, and here's a little tiny region in phase space. And you know how thermalization works, that if you wait a little while, if you have an ergodic system, this droplet will, its volume is preserved, but it will elongate and wrap around. And after a few characteristic times later, that droplet will be spread out into, it'll be like stirring cream into milk, cream into coffee. And so in particular, if I start with 2 points in this region, which are close together, they will end up a little while later very far apart. In fact, characteristically, they diverge. Their separation diverges grows logarithmically. So the separation grows at grows exponentially in time, with an exponent known as the Lyapunov exponent. So this is chaos. The exponential sensitivity to initial the exponential sensitivity to initial conditions is chaos, and it's an essential part of why statistical mechanics works. Now it's interesting because we've known for 40 years that black holes have thermal properties, but it's only in the last year or 2 that people have asked about and identified the corresponding chaotic behavior. So the measure of this separation is, again, we're still classical mechanics. We have the position, say, at time t, and we ask how much does the position at time t change if we change the position at time 0 by a little bit, and that's supposed to grow exponentially. And let me write this as a Poisson bracket. And now let me quantize. Good. And so this is the thing to be looking at. Now, what about quantum mechanics and chaos? So quantum mechanics is linear. So that means if I start with 2 states that are close together in the sense that their state vectors are nearly parallel, they will stay nearly parallel for all times. There won't be any of this exponential separation. But up here, if I consider 2 quantum states, so I just take my classical points and fuzz them out a little bit. I can have 2 quantum states which are orthogonal as states, but which are very close together still and very similar in their physics. And these will still exhibit this exponential separation. And this is what this commutator measures. And so a nice quantity to consider is first you square this take the absolute square of this commutator in order to not worry about sign cancellations, phase cancellations. and then you average it over the thermal ensemble. So a nice measure of this behavior is the trace e to the minus beta h, and then commutator of, instead of calling them P and Q, I'm going to call them W and V, because they might be spins, they might be anything. Okay, and so the assertion is that this quantity will have, let me draw this in the middle because will have a behavior in time that shows initial exponential growth. And if we have bounded operators, the growth has to stop. So let's suppose that. So there's initial exponential growth. And then it turns over and saturates. And it's this initial exponential growth which is the signature of chaos. There's actually two exponentials in the picture. There's the exponential growth initially, and there's the exponential approach to equilibrium. This exponential approach to equilibrium is much simpler. It's known as quasi-normal, or Ruel behavior. And it's been understood for quite a long time in the context of black holes. And then there's this initial exponential growth, which is this thing we're talking about. Okay. Now, so this is the general framework. Now, how does this how does this apply to black holes? So, with black holes, there are kind of two identifiable exponentials. The first of them I talked about in my first lecture, or when I derived Hawking radiation. It's the fact that someone falls through their proper time tau, someone watches them from outside, their proper time t, then partial tau, partial t. Tau is changing by a finite amount when t is changing by an infinite amount, and so this is falling. I think this is the exponent, where beta is the inverse Hawking temperature. So that good. Okay, so here's one exponential that shows up in the properties of black holes. The other exponential is simply if you have a black hole and you throw something into it, you perturb it in some way, it will ring down. Well, it will rather quickly. We kick it. Should draw a foot. Kick it. It'll ring down. It'll oscillate for a bit and then exponentially return to its initial state. So there's two exponentials, and again, this exponential is this quasi-normal behavior. And by the way, you don't need this fancy 4-point function. You don't need this fancy 4-point function to measure that. Any 2-point function will show you the approach to equilibrium. You don't need this. You need that to see this. You don't need it to see this. So this is much more standard. You can see this in a 2-point function. You kick it, you measure. This exponential is in fact the Lyapunov behavior. I drew it as a decaying exponential, but in fact what appears in the observables is the reciprocal, as you will see. And so you actually see a growing exponential. There's another really interesting thing here. So the quasi-normal modes, to find their frequencies, you have to solve a differential equation. You have to integrate over regions of order the size of the black hole itself. They're rather non-local things. The Lyapunov behavior depends only on the black hole temperature. And the black hole temperature, as is well known, is a property of the horizon. It is the surface gravity of the horizon. And so where the quasi-normal behavior is a measure of the whole neighborhood of the black hole, the Lyapunov behavior is seeing right down to the horizon. There's long been a question, how do we know? I give you a CFT, a state, how do you see the black hole horizon if it's there? And we've always said, well, it's thermalization, which is true, but here's a much more precise answer. The way you see the horizon dynamics is through having this Lyapunov behavior. So let me show you let me show you how that happens. So I'm going to outline. So again, this was first done by Schenker and Stanford for a two-sided black hole. And Kitaev did something very interesting with that, which I'll come back to. Partly, he said it applies to both two- and one-sided black holes, but there is something very specific about one-sided black holes which is that if information is not lost, they have an S matrix. That is, there is some unitary mapping from all the states we might have started the system in to the final state, even if we form a black hole in the middle. And what one can do is derive a relation for, let's suppose we have the black hole S matrix. We can derive a relation for how the S matrix changes. So we have a bunch of incoming particles, some black hole forms, and then we have a bunch of final particles. So we have SFI. We can find a relation between the S matrix, a given S matrix element, and the S matrix with one additional particle thrown in. And so this is kind of in the spirit of soft theorems or Ward identities, although I don't know if it's exactly the same. And the basic mechanics is a calculation that Tufte did with Tufte and Dre, and then Tufte on his own in the 80s, I think, yeah. Which is, they said, suppose we have a high energy particle coming out of the black hole, so that it's going to be, basically, suppose we've populated the Hawking mode in some definite way, and now suppose we throw another particle in. Now the point is that sort of the longer, so there's some sort of, twice the Schwarzschild radius. There's some kind of surface here we'll define times relative to. The longer this time difference, the closer to the horizon they meet. You can see that. And the closer to the horizon they meet, the smaller GTT is, because the TT component of the metric goes to 0 at the horizon. And the energy is G upper T times, call it omega 1, omega 2. The center of mass energy squared is basically G upper T times omega 1, omega 2. These are fixed things. These can be of order the Hawking temperature. They can be 10 times the Hawking temperature, some number you choose. But the longer the time delay between when they are here, the closer they meet to the horizon, the higher the energy. And so if we just think about this, so this is a very high energy collision. What happens in a very high energy collision? Well, you know that when you have a rapidly moving charge, its electric field gets Lorentz contracted in this way. Same thing for a gravitational object. It gets contracted into the Eichelberg-Sexel metric. And so the gravitational field of this incoming particle is basically some kind of planar. It's been squished into this plane, and it's a fun bit of just of geometry to show that the net effect. Well, there's different coordinate systems, but in the simplest coordinate system, the net effect of this Eichelberg-Sechsel shock wave on this inflowing particle is to shift it a little bit back, a little bit closer to the horizon. Because it's closer to the horizon, it comes out. It was near the horizon, traveling out. Now it's back closer to the horizon again, and so it's going to take a little longer to get out than it otherwise would have. And so there'll be a perceptible effect. That is, whatever particle would have emerged at some given time will now, whatever particle would have emerged at some given time will now emerge a little bit later. And the amount of lateness grows exponentially in time, again, because the longer this delay, the closer to the horizon they meet, the smaller GTT is, the larger the center of mass energy is. And so this effect grows exponentially after you throw in the particle. And so the relation is then that I'll put a tilde here for delayed. And so the relation is that the S matrix. No, I think I want it on the other. I think I want it over here. That's right. The S matrix with one additional particle is simply the same S matrix as before, but delayed. Now there's a problem because eventually the delay becomes so. Eventually this energy becomes so large that you worry that you would actually form black holes in the collision. But before that happens, something simpler happens, which is the particle is shifted so much towards the horizon, it's pushed behind the horizon and it doesn't get out. So nothing too dramatic actually happens at the horizon due to this growing energy, except that past a certain point, this doesn't make sense. And so what you actually have to do is square and trace. You have to square and trace over late outgoing particles to get a sensible relation. Okay, so there is this relation which seems pretty robust that the black hole S matrix must satisfy, and you can find more details. I just posted another set of notes which doesn't have any more detail except a reference to the original paper 105.0810. So now, two last comments about this. So the first is that Kitaev. So the model that John was talking about. So by the way, this 4-point function that you have to measure to see the Lyapunov behavior is an unconventional one. Almost always in quantum field theory, we can extract any physical information we want, like the S matrix, from the time-ordered endpoint functions. Actually, in high-energy physics, we're not used to thinking about Green's functions that are not time-ordered. But this one, as you see, is not time-ordered. It involves, well, there's a commutator, so there's, it goes t0, 0, various orders. And so one has to calculate something rather unconventional. And we, there are these funny contours, Keldysh contours that you have to use. So this is not an object we're familiar with, but this is the measure of chaos. And this model that John mentioned, which is kind of nice. Well, first of all, it's nice because it's solvable. It's nice because it seems to give one of the ingredients one needs to understand high TC. But also, it exhibits this. It exhibits chaos. It exhibits the exponential growth of this object. And the Lyapunov exponent, I haven't done the calculation, but the assertion is the Lyapunov exponent is exactly equal to the Lyapunov exponent that you get in a black hole from the geometry. And in fact, and this is then something which Stanford, Schenker, and Maldacena have proven, this exponent is actually a maximum. It's the most, if you have a system which is maximally strongly interacting so that it becomes chaotic as rapidly as possible, this is the maximum rate at which that can happen. Tom is shaking his head back there. I'll ask him why in a second. But this is very similar to the viscosity. I won't say bounds, but the fact that for strongly coupled systems, the viscosity to entropy ratio that caused so much excitement in heavy ion physics. This is the same kind of thing. It's even a bit better because, I mean, this proof of Stanford et al. Is something more than I think we really have for the viscosity. So that's rather remarkable that this model of spins, which was designed to do one thing, also does this other thing. And so it suggests that it may in fact be holographic, that it may actually have a bulk interpretation. The Kitaev model is not it's not like the theories we're used to, but it actually has a graphical structure which is not entirely different from a planar gauge theory. So he may have succeeded in finding the simplest holographic model of a horizon. If true, then maybe we can figure out what's behind it. Okay. I think I had one more thing to say. Oh, yes, I did. But first, why were you shaking your head, Tom?
8 over S.
Right, 8 over S. Right, 8 over S. Right. It's very much like the 8 over S story. Well,
All these crazy things go right to the extreme.
right. But they actually have again, I've read their argument, and there are a number of assumptions which may be relaxable. It's true. It may be exactly like 8 over S, but again, it's,
I'm not shaking my head because I think again, it's one of these extreme situations.
Yeah.
That you guys discover and
Then nature seems to go along. Yeah, it's interesting because there's an experimental and theoretical literature on quantum chaos, and there's actually the main focus of that literature is not so much on this exponential growth. It's not an easy thing to measure. The main focus is on things like statistics of eigenvalues. So yeah, this is doesn't get as directly to the heart of that subject as maybe the viscosity did for the heavy ions, but still. Okay, so finally, this is a beautiful story, but there is something very strange about it. Tufts' calculation from the 80s was pretty much ignored by everybody, and it was ignored for what we thought was a really good reason. It's because it's all built around this collision between an outgoing particle and ingoing particle, but there are no outgoing particles. The entire beginning of our discussion was there's an adiabatic principle. The ingoing particle is passing through vacuum, and it leaves vacuum behind by the adiabatic principle. It leaves no effect. The Hawking particles that we're talking about would, basically form later as the vacuum evolves. Well, basically as we translate the vacuum from the infalling coordinates to the asymptotic coordinates, but it's vacuum throughout. This is the Hawking calculation, but if there is a black hole S matrix, that's not true. If there is a black hole S matrix, then these outgoing particles are, although they're statistically the same as in vacuum, they are carrying information because they are, well, we could say because they're entangled with other Hawking particles, or more directly, they're carrying information because they're participating in this unitary S matrix. Their state is correlated with the state of their state is correlated with the states of other things. But that's weird. It means that we're using vacuum fluctuation. It means that vacuum fluctuations are carrying information. Now, vacuum fluctuations can't carry information. They also can't power starships, although if you follow the internet enough, you'll find claims that they can. But they can't power starships. They can't carry information. And in fact, the fact that they are carrying information means that they are not, in fact, they're not vacuum fluctuations anymore. They are not properly entangled with the modes behind the horizon. And in fact, the fact that a TASI calculation now seems to be relevant, and this result seems so simple and robust, it must be true. The fact that TASI calculation is now relevant seems to say that, in fact, the state near the horizon is not vacuum. And this is not a new argument. This is really the firewall argument again. But I've said for 3 years now that my head believes in the firewall because every logical argument that tries to dispel it is so it seems so wrong. But my gut can't believe in the firewall. This is the first time that my gut has believed in the firewall. And it's because my gut says, hey, there's information being propagated there. Therefore those modes are not in vacuum. Yes?
Couldn't you just set a situation include the Hawking computation in the actual precise period of the going?
Right. Well, okay, good. So suppose that we redo the Hawking calculation with this particle. So the Hawking calculation says we don't get an S matrix, we get a dollar matrix. And the dollar matrix doesn't change. If there is an S matrix, it shows this change. In the dollar matrix, where we basically we traced out the state of the interior, there is no effect. And so as there can't be for the reasons. Yeah. Yeah. No, it doesn't, because what you in the Hawking calculation, you have vacuum here. If you delay vacuum, you still have vacuum. The reason that the delay is perceptible is because we've taken the vacuum, we've separated it into entangled pairs, and now we've broken the entanglement and allowed basically ourselves to identify it's because we've broken the entanglement. So no, this is a calculation which in low energy effective field theory can't make sense. Now, the question is how far do you trust effective field theory and where does its breakdown end? But well, good. By the way, there's this ER equals EPR business, which I've never understood for the following reason. Yes, question.
About the top calculation.
Yes.
Was that also in a static black over back?
Yeah, basically the things are happening here.
It's not otherwise it could be the parent.
Well, good. So right. So for a black hole which is slowly evaporating, the event horizon, the causal horizon, and just the horizon where the geometry looks like the horizon is are close together. We could make them very if later on we threw in a whole bunch of mass, the event horizon would suddenly get a lot larger, of course. But right. So they can be very different from each other. But in a sense, it's actually the event. But it's really. Let me actually reiterate in a way that maybe answers the question. The reason. So when you hear chaos, you think about turbulence. You think about wildly, nonlinear things. But the first part of chaos is this exponential separation where things start out similar, end up far apart. And that's exactly, of course, what an event horizon is. An event horizon. So that is, it's a point where geodesics on one side escape and the other don't. So there's a very sharp dependence on initial conditions. And moreover, if you perturb the horizon a little bit, then things will have very different fates than they would have in the absence of the perturbation. So that's real. So it's nothing as wild as turbulence. Although of course, eventually the exponential gets large and we start, wandering over phase space. That's scrambling. That's also interesting, but it's much more complicated. So I guess I really do mean the event horizon for that reason. Yeah. So ER equals EPR, which I think Juan probably explained. I've never understood it because, I've never understood how it's supposed to dispose of the firewall because, so the question is the following. In the two-sided black hole, are these modes carrying information? The statement they're carrying information means effectively they're entangled with other modes that we have in our hands. And for the evaporating black hole, this is true. For the two-sided black hole, they're not, because the other things that they're entangled with have been thrown back into the black hole on the other side. I've never understood that. So ER equals EPR is saying, okay, for the two-sided black hole, we know there's this bridge. Therefore, there should always be this bridge. But in one case, the things you're entangled with are sort of falling into a horizon, whereas in the other case, they're heading away from a horizon. So I think this, I think that this point of view just raises this question: how is the ER equals EPR argument supposed to do away with the firewall? And I don't think there's a real answer there. I think there's more of a scenario. But anyway, so I finished a little early, so I want to make two comments. First of all, it's pretty remarkable that John's lecture and my lecture ended up with the exact same paper by Kitaev, which doesn't exist. even though they seem to be about totally opposite ends of physics, and I just think this is very striking. And also just to comment that I've outlined for you a bunch of scenarios, all of which are ugly. It seems like we're again still in the early days as we were before ADS-CFT, and maybe out of our current confusion, something as nice as ADS-CFT will come again. So thank you. Yes, Ben. Oh, okay, good. Yes. So you have to ask. Good. So this relation is a relation for, again, not actually the S matrix, but the square of the S matrix, and you have to ask whether there is actually a visible effect. And in fact, if you have a typical initial state before the page time, the effect of this tracing out erases the effect. And so this effect actually is visible under exactly the same circumstances as the original firewall argument. The original firewall argument would say that if you repair a very special initial state, then in fact the firewall has to appear sooner. And the same is true for this relation. So actually there's a kind of a nice, it's really the same argument presented in a very different way. Yeah.
So how can you form a two-sided black hole by gravitational collapse?
You're asking me. You should have asked Juan. Did you ask Juan that question? No. So I can tell you what Juan would say, and don't laugh. No, he said this. And he and Lenny said it on a paper they wrote together. And I know from experience when you write a paper with Lenny, you don't always agree with everything that's in the paper. But I think this is the essence of it still. We have a black hole that we form, say, in a pure state. And we let it evaporate until half the bits have come out. So now we have a black hole half as big and a bunch of outgoing radiation. We collapse that outgoing radiation into a second black hole. Now the black hole was entangled with the radiation. It's now entangled with the other black hole. And by manipulating the photons with a quantum computer, we can arrange that these two black holes are exactly in the thermofield state. Now, it seems like a reliable fact that if we allow a black hole pair to form via tunneling, via the Hartle-Hawking process, we will get two black holes, two CFTs, and they will be in the thermofield state. So if the map basically from CFTs to geometries is 1-to-1, then this has to remain true even if we form the black hole not by a tunneling process which very manifestly makes a pair, but by this process of forming one and then forming the second. And so the picture, is that they picture sort of the black hole. They picture the black hole entanglement as being associated with a very tiny wormhole, and then once these collapse, that wormhole sort of becomes large and geometric. And again, it violates the linearity of quantum mechanics for very much the same reason as Papadopoulos and Raju, which is that entanglement is not observable. But it has, this fact, the fact that if you produce the pairs via tunneling, you get this nice dictionary between the thermofield state and the Einstein-Rosen bridge. If you simply take that and assume that things are 1-to-1, then you're led to this much stranger conclusion. Now, actually, Don Marolf and Aaron Wall, before Susskind and Maldacene had considered this possibility and said, no, the answer must be that the map is not 1-to-1, that there is additional bulk data that is not visible in the CFT that distinguishes the different geometries, two black holes versus one. And actually, there is actually a parting thought that I had wanted to mention, which again, the bigger game. So again, this is not a game where the goal is to figure out the answer to this paradox. The goal is to figure out what is a theory of quantum gravity. And something which is missing so far is we have this very precise CFT side of the ADS-CFT duality, and we have the bulk side, which is described only by various approximations, and we've kind of been happy with that. But I think the questions raised by the firewall and the questions raised here really require that we find a non-perturbative description of the bulk. And that's sitting there, as a problem that we haven't made any progress on, in many, many years. Very few people are even trying to answer the question. Tom Banks is trying to answer the question. But I think for a lot of reasons, it seems like there's a very big piece of the theory that we haven't yet found, and I don't even know how to start to look for it except to push on these paradoxes. Maybe it's hidden in Kitaev's model. Anyway, questions? Yeah.
At one point you said we didn't know where Hawking went wrong in his calculation.
Yes.
Specifically. Then you showed the eigenstate thermodynamics hypothesis, and you said the pure state and the mixed state were not differed by non-perturbative corrections. So this means, and Hawking was just using perturbation theory.
Well, let's think about that. Let's think. Right. Yeah. So good. So the non-perturbative corrections there are related to the fact that that there's this fine microscopic structure of states in the real black hole spectrum. In fact, you can rather direct, and so in the limit, in fact, in Hawking's limit, in the limit where, in some sense, the spectrum of the black hole is continuous, that small correction would even go away. And so, another way to try to get a handle on this problem, rather than think about information and infilling observers, is to think about the much more concrete question: how can we find a bulk theory that will give us a discrete spectrum of states? Again, the reason general relativity doesn't give you a discrete. So, if we put a black hole in a box, and now we consider, say, the 2-point function. This is an argument of Vaughan's. We consider the 2-point function for that system. Well, basically, the first operator perturbs it, And because it's a horizon and we're in a box, the longer we go on, there's just a monotonically increasing probability for the perturbation to fall through the horizon. And so the 2-point function falls exponentially for all time in low-energy effective field theory. But if you have a discrete spectrum of states, you can't make something which is exponential. You can't Fourier. Eventually, you start to see that discreteness. You start to see shot noise, I guess. And so you have exponential decay, and then you start to have kind of chaotic behavior of the 2-point function. And so a much more concrete question is to ask, how would you modify the bulk theory to get a discrete spectrum? Yeah.
But the question is, where he went wrong.
No, it's because he was using effective field theory beyond its range of validity, but we don't know what is the figure of merit that says when you're supposed to stop using effective field theory. Yeah. One more, yeah.
So the question about this ER that you do.
Yes, yes.
So in the first thing you said, we have a black hole, and we had some entanglement that came out, and we lost a black hole.
Yes.
So you were talking about entanglement in the gravitational theory, but then after we brought the inside a black hole, the interior, I think of it as like coming from the entanglement between the two states.
Good.
Why is like entanglement in the actual?
Well, let's make a slightly more elaborate version of this, where our first black hole is actually, contained in ADS space. But the ADS space has dual field theory, so we can think of it as something that sits in our lab. And so we collect in our lab the outgoing Hawking quanta. We then have a second copy of the gauge theory, and we feed those into it. So by that means, we can sort of more directly make something which looks like this picture, where we actually have in our lab 2 gauge theories that are in the thermofield state. You're right. In this, if they're simply in asymptotically flat space, well, the questions are sharper in the ADS case. I'm not sure how to pose them so much in the asymptotically flat space. You want to follow up that, or yeah?
I think so, like why was the Hawking radiation important, right? Like, it's the entanglement in the CFT, the wormhole, the geometry. So why, like, what's done if you just add this thing, and then you like turn another thing to entangle with it, so you got.
Right. You could do it in other ways. I could start with just 2 gauge theories in vacuum and start throwing EPR pairs one into one and one into the other. That would also, according to Juan and Lenny, produce this geometry. And again, that would be a conclusion if there is this one-to-one mapping of CFT to geometry. So you have Amir, and then yeah. Right. So the thermofield state, I think everyone agrees, does not have a firewall. But the thermofield state is a very special state of the 2 black hole system. Yeah. So, yeah. Yeah.
So it seems like if you're doing what you described at the end,
Yes.
that seems like a very non-local thing to do as far as
Well, I guess the question is what you mean by non-local. It produces entanglement. It's non-local in the EPR sense. Oh. Well, again, I think it all comes in the end down to the question of if you get to the same final state for the CFTs, does it imply the same geometry in the interior, or is there additional data? Is there somehow data in the bulk that remembers how you produce the system? And I don't see any reason why that should not be true. When you start, you start to assume ADS CFT is a complete description, but we don't know that. And I think I really want to think about all these things from the point of view of having a bulk theory of quantum gravity, but I just don't know where to start with that. Yes.
Couldn't you just understand the process of building the black holes as like really part of the system, and then you have some time to the process? Then it really makes sense that the final state would know about what. Right.
Right, yeah, it makes sense that it would know what happened. Right. It makes it totally makes sense that there would be internal degrees of freedom that remember. Right. I think if you didn't know about ADS-CFT, if you had a bulk theory, you would not necessarily think that the boundary knows entirely about everything in theory. I agree. But you know, it's one more in a list of scenarios that we need a theory for. Yeah. Maybe was there one more question? No. Okay, Henry.
Can I ask about this field double? Suppose someone's managed to build that field double. If one of them got it even a little bit wrong in this part, by
yes.
the time you got to the Einstein-Rosen bridges,
Yeah.
blue shifted the hell out of it, and you destroyed your geometry.
There's lots of actually. So I've kind of refused to think about the two-sided case just because I think there's a lot of confusions like that. That is right. That is. You know, especially it leads you to start thinking about, in some cases, bridges that are exponentially long, and does that make sense? And yeah, I just say, I mean, I think there's something to be understood here. I just don't know exactly what it is. Okay, thank you.
So
yep.
in asymptotically flat
Yes.
geometry, how would you refocus the photons?
You know, I don't know that anybody in the history of this subject ever really discussed how you would do this experiment in asymptotically flat space. You know, it's kind of funny that I think basically until ADS came along, which confines the photons for you. Although they did, actually, it's interesting because there's an interesting point that because you emit so many more photons than gravitons, you actually can distinguish pure from mixed states just by looking at the photons. So that makes your job a little easier. So then maybe you can just use lenses.
Wait, sorry.
Yeah.
Can you think that you can distinguish between?
Yeah. So okay, good. So the emission probability goes down rapidly with the spin of the particle emitted because the black hole is so small in some sense, and so almost everything that's emitted is a photon, or even a Higgs, a spin zero, depending on. And so let's say it's photons. I suppose the photons are more easily manipulated than gravitons. So you can imagine that you could do this. But again, I don't know if anywhere in the literature where anybody has actually described how you would do this experiment in any kind of practical terms. So I think we should stop here. Yeah.
Okay, I had a question if you have any thoughts on how to do something. So
Yes.
we were talking yesterday about this tensor network model that
Yes.
that Harlow has.
Yes.
And we were musing about adding dynamics.
Yes, that'd be
But-
a great idea. Yeah.
So we're not sure. So let's consider you have some 2D spatial slice, and you want to add a time direction. I think a confusion that we had is if you want to have some sort of Lorentz invariance or eventually different variance.
Yes. So there's two questions here. Let me ask you. So we first have sort of one time slice.
Yep.
Now there's two notions of dynamics. There's moving the boundary forward
Right.
and there's moving the slice forward.
Right. So
You
I
probably
think
you
what
pro-
we-
this